Okay, good morning, everybody. My name is Joshua Karasak. I'm the winemaking specialist with Enartis USA. And today we're going to be talking about high pH red winemaking. So if you've never been to one of our webinars before, I'm just going to give you a brief overview of how the webinars work. So first, it's a 40-minute presentation. We usually go from the very beginning to the very end of the presentation without any interruption. So we'll ask that if you have any questions or anything like that during the presentation, that you please hold them to the very end. It's a good idea to have a pen and paper available so that you can write down any questions that you have so you don't forget them during the presentation. If you have any technical difficulties during the presentation, you can use the chat box number 2, which is right over here. If you click on that tab, that'll take you to a separate chat session where you can actually ask for technical assistance, and we'll have somebody there to assist you with that. Additionally, if you're having technical difficulties, a really good way to solve the issue, if you're having any audio or any connectivity issues, is to just go ahead and exit the webinar and re-enter the webinar through your personalized link, and that'll sort of reinitiate the webinar and sometimes fixes some of those connection issues. This is going to be a recorded session, so additionally, if you have any difficulties connecting and you want to be able to watch the presentation later on, we'll have that available online for you. And it is going to be a recorded session, so we ask that during the question and answer section, if you have any sensitive information you don't want to be online, that you please withhold that information until a later time so that we can post this video online without any issues. So just keep that in mind, that this is going to be a recorded session. We do have some attached documents that might be useful to you as well. So right over here, if you click on that folder, you'll be able to access a PDF version of this presentation, our online catalog for 2018 with all of our services and lab services on it. And then also there's a document there for our predictive acid measurement analysis. So that's all available for you there. So this is just a general overview of what we're going to be going over today. So first we'll talk about what determines pH. What are some of the factors that we need to consider for pH, from fruit quality through some of the winemaking processes that might alter or change pH. Then I'll talk about pH adjustments and musts. What are some of the parameters that we need to measure or perhaps consider before making an adjustment, and how we might make those adjustments. Then I'll talk about the microbial impact of a high pH situation. Talk about the oxidative impact in a high pH red wine. And then what are some of the mouthfeel aspects that are associated with high pH wines. So what determines pH? So first thing is fruit composition is probably one of the more important factors that we need to consider. So fruit composition is usually derived from the cultivar, first of all. So what variety are you using? Some cultivars are obviously higher in acidity than other varieties. Some varieties are more prone to picking up certain cations, more like potassium than other cultivars. So the cultivar is going to be really, really important when we consider what the fruit composition, what the resulting pH is. Fruit maturity is really important as well. So depending on what time in the season will depend on what your pH is. In general, as the season progresses, acids tend to decrease, and subsequently also potassium tends to increase in the grapevine. So fruit maturity is very important, and generally the further along in the fruit maturity process that you go, the higher your pH is going to be. Crop level is quite important. The more crop that you have on a vine, the lower the pH tends to be because you're basically dispersing the potassium that would be taken up by the vine into more fruit. So the crop level, generally the higher you go, the lower your pH will be. Soil moisture content during maturity is quite important. So in general, as the soil moisture tends to decrease, the pH tends to also decrease because there's less potassium available for the vine to take up into the fruit. And I've said potassium several times now. That's actually one of the more important parameters that need to be measured, and I'll talk more about that later in the presentation. But just know that potassium is quite important when we consider what the resulting pH is. I mean, obviously acidity is quite important, and several other chemical parameters, but potassium has been found to be quite important when we consider what the resulting pH is going to be. So mineral composition, again, available to the vine. Potassium content, what's available in the soil for the vine to take up. How readily does that vine take up the potassium or cation? And what's the composition of the soil? Are you adding any fertilizer with potassium? And so what's available to the vine is going to also affect what's taken up by the vine. So some of the winemaking considerations. So if we have any acid precipitation, either intentional or natural. So if we are forcing our temperatures lower on our tanks and trying to precipitate some tartrates, or if we have just the natural precipitation of tartrates in a wine, we will generally change the pH to that situation. So generally when we say that 3.8 is a good marker in red wines. Just so happens to be that 3.8 is the maximum or the pKa of bitartrate, which is one of the various forms of tartaric acid present in wine. And at that point is quite important, because if you're higher than pH 3.8 and you have this acid precipitation that occurs naturally or forced, you can have actually a rise in pH. So it's important that when you acidulate a must, or when you add acid to change the must pH, that you need to actually get it below 3.8. Otherwise, a subsequent acid precipitation might actually boost your pH even higher. And then vice versa, when you actually acidulate below 3.8, if you have that precipitation that occurs, you actually lower the pH a little bit more. So 3.8 tends to be a pretty important pH to consider. And if you go below that pH, then a precipitation will lower your pH further. And if you go above that pH, then your pH will rise a little bit more with the precipitation. So it's important to really try and nail down what our final pHs are. And that's why I'm going to talk more about predictive acid panels later on. And then acid adjustments, so the addition of tartaric acid or other acids such as malic acid, maybe even citric acid. Those adjustments are going to change your pH, obviously. And then subsequently, opposite to that, we can also remove acid with potassium carbonate, which in a high pH situation, you don't really think about deacidifying. But in a situation where you might actually add too much acid to try to compensate for high pH, you might actually have to do an adjustment with potassium carbonate later on in the road. So generally speaking, those two different kinds of acid adjustments exist. Pressing is quite important for high pH wines, especially. A lot of potassium exists in the skins of the red grapes. And so after our fermentation has happened and we're pressing out our red must, usually the harder we press, the more potassium actually leaches from the grapes. So with higher potassium, we actually increase our pH more. So sometimes it might be a good idea to separate press fractions if we're making high pH wines. If you want to try to maintain a lower pH, it might be a good idea to separate some of that press cut out, just so that you can segregate them and treat them differently. So more pressing usually generally means higher potassium. And you can see this when you're pressing a wine. Free flow wine, if you're dumping a must into a press, or if you're pumping a must into a press, is oftentimes a much lower pH than the press wine. So ethanol changes as well. The more ethanol you have, the less solubility of potassium bitartrate, and also the more ethanol you have, this also changes the pKa of the tartaric acid. So ethanol is actually important for pH as well. And then malolactic conversion. So this is the process where malolactic bacteria convert malic acid to lactic acid. And that process, you generally deacidify the must. So you actually generally lead to an increase in pH if you are going through the malolactic conversion, but that really depends on how much malic acid you have to begin with. And most oftentimes a high pH must probably doesn't have a lot of malic acid, although sometimes it can in a high TA, high pH situation. So I'm just going to talk a little bit about acid adjustments. Generally speaking, acid adjustments are pretty straightforward. You can shoot from the hip as a winemaker and just try to add 1 or 2 grams per liter, or even 3 grams per liter, or even higher than that. And in general, winemakers will be shooting from the hip because they won't know exactly how much of that acid is going to going to change because maybe they don't know what the buffer capacity is. They don't know a lot of factors, and a lot of winemakers will just shoot from the hip that way, and they'll either over-acidulate or under-acidulate their must, and that generally can cause some problems later on in the winemaking process because you have to go back and make a second or a third addition of acid. You might not get all the way to 3.8, and then you precipitate some acid and your pH goes up higher. So acid adjustments are quite important, and it's oftentimes something that's overlooked by winemakers, but can be fine-tuned up front in order to actually have a better understanding of how the acid that you're adding is affecting the pH, and also can help just streamline the process and make for a better product in the end. So here's just a little bit of data to show what potassium and sodium, for that matter, do in sort of predicting how much an acid add will change the pH. So this is just showing if you were to titrate a solution, let's say a wine, and look at how much, let's say NaOH, or how much sodium hydroxide you used, you would expect a certain amount of acidity from that titrant that you used. And when you do that, you generally, just looking at the amount of titrant and the expected protons from that, you can sort of generate a curve like this. And you can see it's a pretty good curve. A lot of the dots are right on the line right here, and so you can generally predict based off of what you titrate, what the expected acidity is going to be. But if you include sodium and potassium in that measurement, and in that as a factor, you actually can further close in and tighten up those predictions in terms of how much protons you have for a given amount of titrant. So what this basically means is that including potassium in your calculations for your acid adds is actually a really good way to fine-tune and narrow in on your actual acidulation of your must, so that you can actually nail your pHs closer to what you're looking for. So for this, we can talk about predictive acid management, and Vinquery Labs offers a solution for this issue. And basically what we do is we measure pH, Brix, titratable acidity. We look at your organic acid profile with regards to your tartaric acid, your malic acid, maybe even your citric acid, the buffer capacity, and the potassium. And so with those different factors, we have a predictive acidity suite that we use in the lab, which basically takes all of those factors into consideration and can generate a predicted change in your pH for a given acid add. So what that does is it actually, as a winemaker, you submit a sample, a juice sample, and by looking at these different factors and plugging into the suite and generating this number, we can actually tell you how much acid you need to add in order to get to a given pH. So it's a really useful tool, and will really help you dial in your acid adds in the end game. So the benefits of that is that you eliminate second or third additions. You would reduce costs associated with missed adds. So tartaric acid prices, as you can see over here on the right here, you can see tartaric acid prices from 2015 to 2017 did increase a little bit, but from 2017 to 2018, and early 2018, and even the current cost in 2018 has really skyrocketed. So we've seen a double or even tripling of cost. So it's really important that if we want to try to cut back on missed acid adds, so overshooting the acidulation and then having to use potassium carbonate or something later on down the line, using this measurement, we can actually reduce the amount of costs associated with improper adds. And then also the quality associated with improper adds. We want to maintain quality, and we can basically prevent improper adds by using this kind of analysis. Some sampling tips if you're going to be conducting this analysis is we typically recommend after a cold soak or after some sort of soak up to submit your juice sample, because that allows for a little bit of homogenization between the berries and the juice phase, and then you end up with a better number in terms of what your potassium is and what your organic acid profile is. Or after a pump over or mixing, so just basically right after you've mixed a must or a tank, submitting at that point. So I'm just going to talk a little bit about a very difficult situation in winemaking, and that is high pH, high TA. So in the previous example, I talked about acidulating to try to basically reduce your pH. In a high pH, high TA situation, you have very high potassium levels. And what that means is that although you have high TA, you have a lot of acidity. And that acidity actually comes across sensorially as an acidic wine. But you also, since you have high potassium levels, you also have this high pH situation. So you can't acidulate in this situation because you already have a TA that's maybe above 7 grams per hectoliter. And any additional acid additions will make the wine taste sour. So you can't add acid in order to reduce your pH. And in that case, you're kind of stuck with a situation where you have a high pH and can't really adjust it. So now we're just going to talk about the different considerations for a high pH situation, and especially for high TA, high pH situation, because you're kind of stuck with this wine with a high pH. So for a high pH situation, consider that microbes grow a lot more easily in higher pH compared to low pH. And this is probably relatively well known, but just looking at how important the pH is to the growth of just this, let's just look at this data over here with the growth of Leuconostoc strains. We have 3 different strains grown in media with 3 different pHs. And you can see that 2.9 and 3.1 pH, there's almost no growth of this bacteria. But then as we increase it to about 3.3 and even looking at 3.7, you can see a drastic increase in the amount of growth of this bacteria at the higher pH. So what this basically means is that the higher the pH, the more the growth of these bacteria. So basically you're going to be fighting against this microbial pressure more so at high pH than low pH. And this didn't even go higher than 3.7. And consider that for most high pH situations, I'm talking about wines that are above 3.7, even 3.75, I would consider probably the low end of a high pH wine. So microbes grow more readily in those situations, and so we need to consider that. Additionally, I want to talk a little bit about SO2 and how SO2 is affected by wine pH. So here's a little chart that shows the different fractions and forms of SO2 in a wine, or just different fractions given pH. So we have this first line, which this is a line that represents the molecular SO2 form, and you can see it kind of goes right here. And then we have the bisulfite form, which given pH goes sort of up in this region right here. And then we have the sulfite form, which is over here, and there's relatively none of this form available at wine pH. This box right here represents wine pH, this little red square. And this form right here, this molecular SO2, is the fraction that's important as an antimicrobial in wine. So molecular SO2, if you look down here, this line represents the fraction of the form of molecular SO2. And as you increase your pH from, let's say, 3.1 to like 3.5, you can see that the fraction of molecular SO2 is almost non-existent. And then as you increase it even further to, let's say, 3.8 or 3.75, you can see that there's almost no molecular SO2 present. And so that's a problem because that's the fraction of SO2 that's able to actually prevent microbes from growing. So in high pH situations, we have almost no protection from microbes from our SO2. So that's something that's important to keep in mind because in high pH situation, any SO2 we're adding is basically not doing much with respect to as an antimicrobial. Most of that SO2 is going to be in the bisulfite form, which means that it's basically acting to bind acetaldehyde and things like that. So it's still useful in red wines, but it's not going to be acting as a strong antimicrobial. So now I'm going to talk about a really useful tool that's available right now for winemakers to use, and that's called Sal Micro. So Sal Micro is, I think, a really great product for high pH situations. Sal Micro is a pre-activated ketosane, and so ketosane is a polysaccharide that's derived from a fungus called Aspergillus niger, and our version of ketosane is pre-activated, which means that we go through a step of acidulating and grinding the ketosane under very, very high pressure. And basically what that does is it activates the ketosane. It charges the surface of the ketosane and gives it more activity and better activity for what it does. Ketosane is an antimicrobial fining agent, which means that basically, like any fining agent, it removes something from the wine that you don't want to be there. And in this case, it's microbes. So it's broad-ranged activity, which means it can work on bacteria, it works on wild yeast, it works on Brettanomyces, it works on all different kinds of forms of microbes. It can be used at nearly any phase of the winemaking process. So we can use it in the must, we can use it in a juice, we can use it in the fermentation, we can use it just after fermentation, we can use it in aging. So it's very versatile in terms of its application in the process. And the reason that we can use it in the fermentation is because it has negligible impact on active Saccharomyces cerevisiae. So basically, if we have a population of Saccharomyces cerevisiae, it's not going to disrupt or destroy its activity like other microbes. So that's why we can use it in the fermentation and makes it particularly useful for that purpose. It is a vegan product to use, so you can use it and have a wine classified as vegan. It's non-allergenic, and it works well at high pH. So that's what makes it particularly useful for this conversation, in that we can't use SO2 as an antimicrobial, but we can use Stab Micro as a way of eliminating the pressure that comes with a high pH situation. So it's not affected by pH, and you're able to use it at high pH. There are two different versions of this. We have Stab Micro, which is just the pre-activated ketosane alone. That's used for clarified wines and wines that are aging. For the Stab Micro M, that's used for musts, and so we want to use that in the juice or in the must, and we can use it in the fermentation. Anytime you have a turbid wine or juice, that's where you want to use the Stab Micro M. And that's Stab Micro with a little bit of yeast derivatives, as well as an activated chitin. So it's basically a blend that's used for high turbidity situations. So this is how Stab Micro typically works in the process. You have a tank or some sort of vessel with wine or with must in it. You would add the Stab Micro, mix for usually a half hour, or get some mixing on the tank for at least a half hour. And then basically what happens in that process, where we have a half hour mixing, is that the chitosan, as you can see in this close-up, this is an electromicrogram of ketosane up close. So this large sort of looking asteroid thing is the Stab Micro. And you can see these little dots stuck to the surface of it. That's actually Brett. So you can see that it's important for this compound to contact the microbe, because it sticks to the surface of the chitosan. And then basically what happens is it settles out to the bottom of the tank. And you can then rack off the top of the tank and remove any of the bacteria and yeast that are stuck to the chitosan. Alternatively, you can also leave the chitosan in the tank for a little while if you like. It's not going to have any negative effect. We do recommend racking off though if you're able to. So now I just want to look at some of the effects of Stab Micro on different wine microbes. So you can see Brettanomyces, Lactobacillus, Pediococcus, all of these yeast and bacteria are able to be decreased with increasing dosages of Stab Micro. So this is the control of Brettanomyces, and you can see it's got quite a high population. And then with as little as 2 grams per hectoliter and even 5 grams per hectoliter, we're able to knock the levels of Brettanomyces way down, almost nothing. And then with 10 grams a hectoliter, we're pretty much eliminating any Brettanomyces populations. Lactobacillus, we see a similar thing. A low dosage of 5 grams per hectoliter is able to knock down most of the Lactobacillus. Pediococcus, similar thing, 10 grams per hectoliter, we're able to knock out most of it. Acetobacter, we usually have to use a little bit higher dosage, so consider 20 grams per hectoliter as a maximum dosage, and you can still eliminate Acetobacter with that. Zygosaccharomyces, you can also kill Zygosaccharomyces with Stab Micro. And then this is just looking at malolactic fermentation. So the nice thing about Stab Micro is that you can actually still go through the malolactic fermentation after using Stab Micro. So these are 3 different treatments. We have a control, We have a treatment with 10 grams per hectoliter Sal Micro. That's the purple line here. And then we have a 20 grams per hectoliter treatment and this blue dotted line up here. So the nice thing is that you can actually completely eliminate the likelihood of a malolactic fermentation with a high dosage of Sal Micro. But then with a moderate dosage, you can actually still continue to have a malolactic conversion. So it might be a little bit delayed, but you can actually have the malolactic conversion still happen. And this is still a fairly high dosage. 10 grams per hectoliter is quite a high dosage of this product. So what that means is that if we didn't want the malolactic conversion to happen, we could use it at a high dosage. If we did want it to happen, we can still use it in the fermentation with a moderate dosage and have the malolactic conversion happen. So it's nice flexibility with the dosage there. So now I'm going to talk a little bit about sluggish fermentations due to competition. So competition is oftentimes a big factor in high pH wines because, again, there's a lot more activity of bacteria and yeast in high pH situations, so there's more competition. And so with high pH situation, you have more competition. And one way that we can deal with that competition in a sluggish situation is actually use Sal Micro. So here we see a fermentation, and we've seen this happen several times. We have a lot of different fermentation kinetic curves showing the same result, is that when we have a fermentation that looks like it's going pretty well, at around 5 brix, it starts to slow down. And then we recommend the winemaker at that point to make a Sal Micro M addition. And then at that point, you can see that the fermentation kicks back again and the brix start to drop again. So this is a really handy tool if you start to have sluggish fermentations to try and get things kicked off again. Similarly, we have another thing that can help in a struggling fermentation. So we again need to try and give our Saccharomyces as much of an advantage as possible in a difficult fermentation condition. And another way to do that is increase survival factors. So our Nutrifirm No Stop is a yeast derivative that's basically a yeast hole that's specific for trying to get fermentations to continue. And it does this by having a blend of yeast holes that are rich in sterols. And the sterols basically act as components of the yeast membrane that help the yeast survive in high alcohol situations. So between these two products, you can use them preventatively actually in a fermentation. If you were around 10 brix, you could treat with some Nutrifirm No Stop, even use a Sal Micro treatment, and you could drastically increase your likelihood of going all the way through fermentation without getting stuck. And then also they can be used as a curative situation. So if you start to slow down or get stuck, you can use a little bit of No Stop, or you can use some Sal Micro M or both to try and get things to push along without actually having to do a complete restart, which can be a real pain, especially during harvest. So now I'm just going to talk a little bit about tannins as antimicrobials. So this is another tool that winemakers can use in a high pH situation to actually decrease growth of bacteria. So this is the effect of tannic acid on Lactobacillus plantarum cells. And you can see here, this is the amount of CFUs per mil. So this is the amount of growth essentially. And these are different treatments. So all these lines represent a different treatment. So we have a control. We have an ethanol treatment where they increase the ethanol by 3%. We had an addition of caffeic acid, addition of ferulic acid, or the addition of tannic acid. And this tannic acid is actually gallic tannin. So you can see that all the other treatments had relatively strong growth, but the tannic acid treatment actually was significantly slower growth because the tannic acid was actually able to inhibit some of the lactobacillus growth. So tannin can act as another way of limiting or decreasing the growth of bacteria. And so this could work on a machine harvested fruit if you have a long distance for machine harvested fruit in transit, or and freshly crushed grapes. Let's say if you're going to do any kind of soak up or anything like that, adding a little bit of tannic acid can help keep the grapes stable in that soak up. So here's an example of a cold soak must where we had a control and we had a treatment with Tan Blanc. So our Tan Blanc is a tannin of gallic tannin. And so we have this treatment here, the control, and the Tan Blanc. And you can see that over the course of 7 days, the amount of growth of this, and this is actually a lactic acid bacteria, lactobacillus. And you can see that the growth of the lactobacillus is much higher in the control than it is in the tan blanc treatment. So again, just another way that Gallic tannin can help. In red wines, the tan rouge is probably a more appropriate, another way that Gallic tannin can help. In red wines, the tan rouge is probably a more appropriate use because it's a sacrificial tannin, so it helps protect color and protect phenolics, but it also has a little bit of Gallic tannin to help in this situation with decreasing the growth of lactobacillus or other lactic acid bacteria. So tan blanc and tan rouge can both be used in this case. So now I'm going to switch a little bit and talk about oxidation and high pH situations. So oxidation at high pH is actually much different than at low pH. Wine phenols tend to oxidize faster at high pH. And the amount of phenolate ion, which is related to oxidation, is 9 times higher at pH 4 compared to pH 3. So what that basically means is that wines at higher pH tend to oxidize faster than wines at low pH. And we saw this in data that was derived from Singleton's study of this in 1987. He looked at regular acid conditions, and we looked at a wine that was made alkaline. And this is a really extreme situation where they basically bumped up the pH to like pH 8, I think. So it's an extreme situation, but it showed basically that at higher pH, that wines oxidize faster than at lower pH. So they showed this inherently in the study, and it's been proven since then that wines at high pH do oxidize faster. So the other factor to consider here is that the amount of phenolics that you have in a high pH wine, the phenolics are actually less efficient at scavenging oxygen than in a low pH situation. So your phenolics are less efficient at resisting oxidation than at a higher pH. So your phenolics are basically less efficient at high pH. Another factor that we investigated was looking at antioxidant activity of ketozan. So this study was done by Cecchini and Raponi, and basically they looked at different treatments. They had a treatment of ascorbic acid, glutathione, chitosan, and SO2. And basically what they did is they looked at the evolution of color and oxidation that occurred. So this was in a white wine, and what they saw was that this treatment, the chitosan, had the least of evolution of color, of yellow tint, and basically the less amount of oxidation compared to the other treatments. Even SO2, which was much higher, and ascorbic were less efficient at limiting oxidation. So what this basically points to is that ketozan has some antioxidant activity. So while this was done in a white wine, this sort of idea interested us, and we wanted to look at how it would affect high pH red wine. So we have a device in our lab called the Calyx Machine, and this is a analysis that's available commercially right now. And basically, the Calyx Machine measures redox potential and has a special measurement called Calyx. And the redox potential basically points to what the redox state is of the wine and what the redox potential is. The Calyx number is a measurement that basically looks at how resistant the wine is to oxidation. And so basically, in relative terms, what these measurements mean, in a situation where you have a high redox state and a low Calyx state, you have a wine which is at risk of oxidation. In a wine that you have a low redox state and a low Calyx number, you have a wine that's not stable because one, it's in a very low reductive state, but it also has no resistance to oxidation, so it's in a state where it could become oxidized. In a situation where we have a low redox number and a high Calyx number, this is a wine that's considered stable because it's in a low redox state and it has high resistance to oxidation. And then in a state where you have a high redox and a high Calyx number, we say that this wine is ready to drink because it's in an oxidative state, but it also has a lot of resistance to oxidation. So we say that one is ready to drink. When we did some treatments for high pH wines, we saw the same results repeatedly. And we compared basically in this measurement a control with a 20 milligram per liter SO2 addition and the addition of Sal Micro M at 30 grams per hectoliter. And what we found from this analysis is that compared to the control and the 20 milligram per liter of SO2, the Sal Micro addition had a lower redox potential and a higher Calyx number after the treatment. And basically what that equates to, if we look back over at what the Calyx number means, is that we have a lower redox number and a higher Calyx number compared to the control and to the SO2 addition, which makes the product more stable with respect to oxidation. So what this basically points to is that Sal Micro and Ketozan is an additional tool for limiting oxidation in both white and red wine. So it has some antioxidant activity as well. Other solutions that we can use for oxidation. So because our phenolics are less efficient at limiting oxidation, increasing the amount of phenolics that we have is important. So the more phenolics that we have, the more oxidative protection we're going to have. And so increasing those phenolics is going to be important. And we can do that with extraction enzymes and different forms of extraction. Basically any way that we can get some more phenolics out of the skins and maybe a little bit out of the seeds, that's going to help prevent oxidation and oxidation of aromas. And then limiting oxidation during aging is important as well. So we can do this with Surly products. So our Surly 1 is a yeast derivative, yeast cells that basically scavenge oxygen and provide mouthfeel or mid-palate. So in the aging process, we can actually use yeast lees to scavenge oxygen. And you can use this, actually, you can use active lees from your fermentation. If you have a clean fermentation, you can use some of those lees. If you have a fermentation that maybe wasn't so clean, you might want to rack off of those lees and use something like Surly 1, which is a clean lees. And basically, those lees are able to soak up oxygen and scavenge oxygen from solution. So this is another way of basically limiting oxidation in the aging process. So using these two products can really help in the with the oxidation in a red wine. And then finally, I just want to touch on the pH impact on astringency. So this is the last thing I'm going to discuss with pH. So obviously more things that we could talk about, but we're limited by time in these webinars. So the pH impact on astringency. So what was found in 2008 from Fontaine is the lowering of pH actually increases the perception of astringency. So for the same amount of tannin that we have in a wine, a lower pH will actually increase perception of astringency. We also know that lowering the pH increases reactions with protein and tannin. So basically what that means is that your saliva has proteins in it and your wine has tannin in it, and basically those proteins in your saliva are more interactive with the tannin in the wine and will force more astringency at a lower pH compared to a higher pH. So higher pH wines tend to be a little bit softer in astringency for the same amount of tannin as low pH wines. So kind of an interesting thing to keep in mind is that if we are extracting more phenolics, we might be getting more phenolics out of the grapes. We might not have as much astringency as let's say a lower pH wine. So kind of an interesting thing to keep in mind. That pretty much does it for the webinar. I'm just going to go through some conclusions, what we may have derived from this presentation. So dealing with high pH wines requires a different mindset from typical pH wines. We need to treat wines a little bit differently with high pH compared to regular pH. Microbial influence is higher at high pH situations, which may require extra care, higher sanitation, and use of products like Ketozan to help supplement and reduce the amount of impact from microbes. Tannins can benefit high pH wines as antimicrobials, as with galactannin, and antioxidants, as with condensed skin or seed tannin. And then oxidation occurs more readily in high pH wines, so increasing phenolic levels and utilizing yeast lees can help sort of buffer those situations. So thank you very much for your participation in the webinar. I really appreciate your attention and joining us this morning. I'll ask you please fill out our survey if you can. We're going to send out an email after this webinar is finished, and that'll have a survey in it. And if you could please take a couple minutes to let us know how we're doing with the webinars, anything that you might change. We would love to hear your feedback on that. We do have, again, the useful downloads over here in this folder over there, so be sure to use those and download those if you can. Don't click this link yet because it'll take you out of the webinar, but if you right-click this link and open it in a new window, that'll take you to our Focus On tab, where we actually have more webinars and more useful information that you can check out. There's a lot of really useful info there and webinar recordings that you can use that are pretty interesting. We do it on all different kinds of topics. Now, if you want to, I'm going to open up this chat box a little bit more. And basically, we can do a 20-minute question and answer portion now. So any questions that you have on the content we talked about today, I'll be happy to answer them for you. You can type all your questions over in this chat box over here on the left, and I'd be happy to answer them for you. So we'll take 20 minutes now to do our question and answer. And I just want to say thank you, everybody, for attending. And now I'm happy to take your questions.